Section 16.6, Parametric surfaces and their areas. Suppose that r of uv equal to x of uvi plus y of uvj plus z of uvk is a vector-valued function defined on a region D in the uv plane. So x, y, and z, the component functions of R, are functions of the two variables u and v with domain D. The set of all points x, y, z in R3 such that x as a function of u and v, y as a function of u and v, and z as a function of u and v, as uv varies throughout D, is called a parametric surface S, and the equations are called parametric equations of S. The surface S is traced out by the tip of the position vector r of uv as uv moves throughout the region D. So this is very similar to the way that we traced out curves using parametric equations. Our vector would point to a point on the curve, and then it would point to another point, and another point, and another point, and it would trace out the entire curve. Well, pretty much the same thing here. We're going to point to a point on our surface, we point to another point to another point, and we point to every single possible point on the surface. So as an example, how about we identify and sketch the surface with vector equation 2 cosine u I plus vj plus 2 sine uk. So how about we say that x is equal to 2 cosine u, y is equal to v, and z is equal to 2 sine u. Then notice if we take x squared and add it to z squared, we get 4 cosine squared u plus 4 sine squared u. And we factor out the 4, cosine squared plus sine squared is 1. 1 times 4 is 4. So x squared plus z squared equals 4. Well, that's the equation of a cylinder with the axis the y-axis. So let's see if we can draw that. So actually, how about I do these lines for my cylinder first? Maybe this will come out better. And I can do maybe something like this. I don't know if I wanted it that long. Yeah, maybe a little bit smaller. Okay, and I'll close up my cylinder and I'll put in some axes. So that can be the z-axis, and then it kind of cuts through for the y-axis and my x-axis. So let's have the x-axis poke out. Okay, so it looks like it intersects the x-axis when y and z are 0. So that would be when x is 2. So this is the point 2, 0, 0. And similarly for z, that would be the point 0, 0, 2. Notice all of these circles are x squared plus z squared equals 4. These little cross sections that we get. So that's our surface, our parametric surface. If a parametric surface S is given by the vector function r of uv, and we keep u constant by putting u equal to u naught, then r of u naught v becomes a vector function of the single parameter v and defines a curve C1 lying on S. So that's where we set u equal to u naught. That's this green curve right over here, and it becomes this green curve on the surface over here. That's where we're just have constant u. So then if we keep v constant, let v equal v naught, then we get a curve C2 on the surface, given by r of u v naught. We call these curves grid curves. So how about we use a computer algebra system to graph the surface that we're given over here at example 2, and we'll see which grid curves have u constant and which ones have v constant. So let's pull up our handy-dandy grapher, do a 3D graph, and how about we do one of the templates they have is for parametric. There we go, Cartesian surface, parametric. And for x, we will put in 2 plus sine of v. Oh, we have to do that in parentheses though. So let's put that in parentheses first, 2 plus sine v, and then multiplied by cosine u, that's x, and then for y, we'll do 2 plus sine v times the sine of u, and then for z, it's u plus cosine v. Notice the default parameters they have over here are t and u, so we have to switch that to u and v. And hit enter. Oh, beautiful. We have this like 3D kind of helix curve. Let's see if we can go a little bit below though. How about we start at, say, -10 for each of these guys. Oops. -10. Okay, cool. So let's see if we can grab this. Let's see, here's our x, y, and z axis, so I think this is a good place to grab it. And we'll make this much smaller. Much smaller. Okay, that's pretty good. I'll take that. Okay, so which grid curves have u constant? Which ones have v constant? Well, v constant is a little bit easier. Notice that if v is constant, then this is some constant times u. This is cosine u. This is some constant times sine of u. These are the only variables now. So cosine sine, and then v is constant. So this is also just u plus a constant. That literally just looks like our helix. So we could say that if v is constant, then that implies that sine of v and cosine of v are constant, which, as we've seen when we did parametric curves, is our helix. It was cosine, sine, and then z. So if the v constant grid curves are the helix ones, then that means that there are these like curves that go like this. So each of these little like bands, you can see they're alternating colors, but these would be the grid curves for v being constant, those slices like that. So that means that the other curves, these curves, should be the ones where u is constant. So all of those are little circles. So we could say that u is constant means that we get circles. You can even kind of see that if you set u equal to constant, then this becomes some constant times sine, some constant times sine, and then we have cosine, sine, and cosine together. Maybe you can imagine that you end up with a circle. But in any case, you can do it kind of by looking at v first, if you want to look at the graph. How about we find a vector function that represents the plane that passes through the point P0 with position vector R0, and that contains two non-parallel vectors a and b. Let's start with P0, and we'll draw vectors a and b, and we'll draw, let's see, it has to point to some point P also. So how about this is a point P it points to. So it points along over here. And it's going to have containing two non-parallel vectors a and b. So let's say that this is b and then this could be a. Okay, notice that a and b don't quite reach the parallelogram that would contain this thing over here, like to get to p, so we need to extend them a little bit. So how about we say that in order to get from P0 to P, we could build a vector from P0 to P. If we scale a and we scale b by some scalars. So how about we say that u times a plus v times b would get us to from P naught to P. So what we're saying is we'll take, how about some other color, and we'll extend B, maybe a little bit like this. Maybe that was a little too much. So then we'll call this V times B, and we'll extend A so that we can get to P. We'll call that U times A. So we end up with like this little parallelogram. Well, it should have been a parallelogram, but I made this UA a little bit too long. Let's see if I can make it shorter. Erase. Make it a little bit longer, a little bit shorter. It's a little bit better of a parallelogram. The idea is that A and B are vectors that are inside of our plane, but they don't necessarily reach another arbitrary point that we get from our starting point. So in order to get there, we probably have to scale them some amount. But if we scale them by some amount u and v, then we'll be able to get to any possible point we want, as long as we move up a certain amount, and as long as we move left or right a certain amount. So that means that we could say that the position vector r, let's say, could be the vector that goes from the origin, let's say the origin's over here, so it points at P. So that means that r is going to be the vector that points at anywhere in our plane, any point, and it builds our plane for us. Well, the way that we can build r is by first pointing at P naught, and then going from P naught to P. And then those two vectors added together, tip to tail, would equal r, this guy. So how about we do that? We'll say that r is equal to the vector from the origin to P naught, added to the vector from P naught to P. And the vector from the origin to P naught is just the position vector of P naught, which is r naught. And then we said that P naught to P was UA plus VB. So that means that our position vector for any point in our plane will have two parameters, u and v, and it'll be r naught plus UA plus VB. So let's say that we set r equal to xyz, because for our point P, we probably want it to have coordinates xyz. We would probably want r naught to have coordinates x naught, y naught, z naught. So then we could set A to have coordinates A1, A2, A3, and we could set B to have coordinates B1, B2, B3, and we can get parametric equations x equals x naught plus UA1 plus VB1. All I did was take this equation and just split it for x, and now I'll split it for y and get that y is y naught plus UA2 plus VB2, and then z would be z naught plus UA3 plus VB3. So we've come up with a vector function that presents our plane, and we even came up with parametric equations that represent our plane in terms of two parameters. How about a parametric representation of the sphere? Well, remember that x squared plus y squared plus z squared, that was rho squared in spherical coordinates. So this is the equation is the same thing as saying that rho squared equals a squared, and taking square roots, we see that rho equals a. Remember, rho always has to be positive. So that means that we could say that x is a sine phi cosine theta, because x is rho sine phi cosine theta in spherical coordinates, and y is equal to a sine phi sine theta, and z is a cosine phi. So we have a vector function r of phi and theta. We have two parameters. It's going to be a sine phi, cosine theta, and that'll be our ith component. A is some constant because we're doing parametric equations to represent a sphere of some constant radius. And then we're going to do a sine phi, sine theta for j, and a cosine phi for k. Remember that phi goes from 0 to pi in spherical coordinates, and theta goes from 0 to 2 pi. So this means that we could write our domain as the interval from 0 to pi crossed with the interval from 0 to 2 pi. So if we were to draw that, it would look something like this. Let's see. So here would be phi, here could be theta, phi goes up to pi, but theta goes up to 2 pi. So it's a bit of a rectangle. So this could be our domain D for our parameters. If we look at what happens with R, then R takes this domain, all of these possible thetas and phis, and it spits it out onto a sphere. So let's see if I can maybe draw that. Yeah, big maybe. So let's say here's the z-axis. Where do I want to put my y? Okay. And I need x. How about I make x poke out? Like that. Can make y even poke out a little bit too, why not? So then if I have, let's put a little perspective over here. Put there. So now it looks a little more 3D. So if I have, say, some phi equal to constant. So it's like x equals constant. So we get a vertical line in our domain. So notice that that phi equals constant becomes one of these circles. When we map it through with R, we just get one of these guys. So this is for phi equal to some constant c. Notice this circle over here, the equator is also phi equals some constant c, different constant c. So how about I put, oh, I almost forgot to put my origin, doesn't really matter so much though. How about I put if theta is a constant. So let's see, I need another color. How about I make this for constant theta? So I'll make this theta equals k because I already used c. So then over here on the phi axis this is c, and over here on the theta axis this is k. Let's see what happens when we take our theta equals k line. Well, as you might expect, we get a meridian. We get a semicircle. So that's theta equals k. So all of these lines, theta, phi equals c and theta equals k, they come up with a whole bunch of circles and a whole bunch of semicircles that all together build up our sphere. Let's find a parametric representation for a cylinder, x squared plus y squared equals 4, where z goes between 0 and 1. While spherical coordinates work so well for our sphere, how about we use cylindrical coordinates for our cylinder? In cylindrical coordinates, we have x squared plus y squared equals r squared. So that means that r squared equals 4, so r equals 2. So that means that x is equal to 2 cosine theta, r cosine theta, and y is equal to 2 sine theta, r sine theta, and in central coordinates z equals z. We still have theta between 0 and 2 pi, and as they told us, z would be between 0 and 1. So it looks like our parameters are theta and z for our cylinder. How about a vector function that represents the elliptic paraboloid z equals x squared plus 2y squared? Well, in this case, we have z already written as a function of x and y. So we already have two parameters given to us. We can just set x equals x and y equal to y. We don't even have to use u and v because z is already x squared plus 2y squared. So we already have everything in terms of just two variables. So that means that our vector function r can be written as r of xy instead of r of uv, and that'll just be xi plus yj plus x squared plus z squared k. So how about we find parametric representation for the surface z equals 2 times the square root of x squared plus y squared. So it's the top half of the cone, z squared equals 4x squared plus 4y squared. Again, we have z as a function of x and y, so we can just set x equal to x, y equal to y, and z equal to 2 times the square root of x squared plus y squared. So that means that r of xy becomes xi plus yj plus 2 times the square root of x squared plus y squared k. Notice this is not the only way we could do this, though. We have a cone being represented, so we could do everything in terms of polar coordinates, r and theta. So if we wanted to use r and theta as the parameters instead of x and y, we would have x equal to r cosine theta, we would have y equal to r sine theta, and we'd have z equal to the square root of, oh, I forgot my 2. 2 times the square root of x squared plus y squared, which is 2r. So then we'd have r as a function of r theta. Notice this is the vector r, this is the polar radius r. So we have r cosine theta I plus r sine theta j plus 2r for z k. So in this case, our parameters are r, which is greater than or equal to 0, and theta, which goes between 0 and 2 pi. So lots of different ways we can parametrize surfaces, just like there's lots of different ways we can parametrize curves. Next up, surfaces of revolution. They can be represented parametrically and thus graphed using a computer. For instance, let's consider the surface S obtained by rotating the curve y equals f of x, where x goes between a and b, about the x-axis, where f of x is greater than or equal to 0. Little typo over there. Where f of x is greater than or equal to 0. Let theta be the angle of rotation as shown in the figure. So we've got some y equals f of x in our plane, and then we rotate it around the x-axis. So notice that this distance is f of x, this distance is f of x. So we can let x be the parameter x equals x. Theta is our angle of rotation. And then z is just going to be f of x times sine of theta by looking at this triangle. And y is f of x cosine theta, because y is our adjacent side. So we get just x equals x, y equals f of x cosine theta, and z is f of x sine theta. So we take x and theta as our parameters, or make these our parametric equations for s. So our domain is given by x going between a and b. That tells you how long we have our rotation going for. and theta going between 0 and 2 pi, how much we want to rotate for our surface of revolution. So how about we do an example, and we'll find parametric equations for the surface generated by rotating the curve y equals sine of x from 0 to 2 pi for x about the x-axis. So what we'll do is we'll set x equal to x. We'll set y equal to f of x times cosine theta. So that'll be, in this case, sine of x times cosine theta. And then z will be sine of x times sine of theta, because it's f of x sine of theta for z. So we have x going between 0 and 2 pi. We have y going between, or theta going between, 0 and 2 pi also. So how about I try drawing this using a little bit of perspective change. We'll put z over here, but we'll put y out over here. That way I can show you the revolution taking place over the x-axis. So if this is the x-axis, we need to draw our curve. Remember, we're rotating y equals sine of x. So that's like something like this, our sine function. But then it rotates all the way around. So it rotates all the way around at every single little point. So we should get like a complete 3D version. It kind of looks like little beads, if you can imagine that. It's a 3D version of our sine curve formed by rotating it around the x-axis. Next, if S is a parametric surface traced out by a vector function r of u v, then at a point p0 with position vector r of u0 v0, if we keep u constant by putting u equal to u0, then r of u0 v becomes a vector function of the single parameter v. So it defines a grid curve as we've seen in C1. So that's when u equals u0. But then the tangent vector to C1 at p can be obtained by taking the partial derivative of r with respect to v. So that would be this guy over here. So that means that we're taking the partial of each of the components, partial of x with respect to v, partial of y with respect to v, partial of z with respect to v, and we do that at the particular point u0 v0 that we're talking about. So then if we do the same thing by keeping v constant, set v equal to v0, we get a grid curve C2, as we've seen, and that means that we get a corresponding tangent vector r of u. Remember, we're taking it with respect to u because we're saying that v is the constant. So that means that its tangent vector is each of these partials with respect to u for each of the components. So what we can do is, we could say that if the cross product is not 0, then our surface is called smooth. And for a smooth surface, we can build a tangent plane out of these vectors. So that tangent plane is the plane that contains our tangent vectors RU and RV, and the vector RU cross RV is a normal vector to our tangent plane. So it kind of pokes out. Remember, our cross product is perpendicular to both of the vectors that go in. So now we have a normal vector to the tangent plane, RU cross RV, so we have a way of building the tangent plane. So let's do an example of that. We can now find the tangent plane by taking the cross product and using that normal vector and a point to build up our plane. So how about we find these vectors RU and RV? So RU will be the partial of x with respect to u times I plus the partial of y with respect to u for j, and the partial of z with respect to u for k. So that'll be, in this case, 2ui, and then this is just v squared for y, so when we take the partial with respect to u, it disappears, so we don't have any j's. And then for z, the partial is just 1, so we just get k. Let's do the same thing to get our partial with respect to v. So that would be partial of x with respect to v plus the partial of y with respect to v for j plus the partial of z with respect to v for k. And and that'll just be 2v for j. Notice now the I component is 0 plus 2k. So now we need the cross product to find our normal vector. So our cross product RU cross RV is equal to, let's see, we got I, j, and k for our cross product. And then for RU, we've got 2u and 0j, and then 1k, and then we've got 0i for RV, and then 2v, and then 2 for k. So that means that our vector becomes minus 2vi minus 4uj plus 4uvk when we take our cross product. So we're supposed to do this at the point 1, 1, 3. So at 1, 1, 3, notice that means that 1 is equal to u squared, 1 is equal to v squared. So u is equal to plus or minus 1, v is equal to plus or minus 1, but z is u plus 2v, and z is supposed to be 3. So that means both of them are positive. So we have u equal to 1 and v equal to 1. So that we plug that in, we can get our normal vector now. We plug that in for this guy. We see that our normal vector at the point 1, 1, 3 will be minus 2i minus 4j plus 4k. Okay, perfect. So that means that we'll take n, we'll dot it with our r minus r naught. So that means that n becomes our coefficients, minus 2 times x minus our x value, 1 minus 4 times y minus our y value of 1, plus 4 times z minus our z value of 3. That'll be equal to 0. That's our equation of our plane. And if we want, we can rewrite that as x plus 2y minus 2z plus 3 equals 0. Next, if a smooth parametric surface S is given by the equation r of uv equals x of uvi plus y of uvj plus z of uvk for uv and d, and S is covered just once as uv ranges throughout the parameter domain, then the surface area of S is the double integral of the length of the cross product. Remember that the length of the cross product, the magnitude of the cross product, is the area of the parallelogram. So you can imagine that the parallelogram that sits tangent to this thing has some sort of area. We stack up all of those areas and we get the surface area of the surface, exactly like you'd expect. And this is very similar to the way that we found the length of the curve by taking the length of r prime and then adding up all those little pieces. So it's very similar to, parametric surfaces are very similar to parametric curves. So how about we do an example of that by finding the surface area of a sphere of radius a. So as we've seen, we can parametrize our sphere by writing x equal to a sine phi cosine theta, y equals a sine phi sine theta, and then z equals a cosine phi. So then we have d equal to all of the phis and thetas such that phi goes between 0 and pi, and theta goes between 0 and 2 pi. So this means that r phi crossed with r theta will be our normal vector. So that's going to be I, j, k, and we'll get the partial of x with respect to phi for r phi, partial of y with respect to phi, partial of z with respect to phi. And then the same thing for r theta. So x theta, I just did x twice, I need y. And I want this to be equal to, let's see, do I should probably write that after because this is going to be a little bit long. So how about I do my second row first? I take my partial of x with respect to phi. So I'm looking at this guy over here. So this is constant. So I just get derivative of sine as cosine. So I have a cosine phi, cosine theta. And then partial of y with respect to phi. So that'll be a cosine phi, sine theta. And then for z, minus a sine phi. And now I'll put my i's and j's and k. Okay, so now I'll have minus a sine phi, sine theta for all of the partials now with respect to theta. So then a sine phi, cosine theta, and 0. Because notice there's no thetas in there. So then this works out to a squared sine squared phi, cosine theta. For I, we take our determinant, plus, because minus minus plus, a squared sine squared phi, sine theta for j, plus a squared sine phi, cosine phi for k. And now we need to take the length of this thing, because that's how we get our surface area. So the magnitude will be, let's see, we're going to have to do each of these guys squared and take the square root. So I'll square them first. A to the fourth, sine to the fourth, phi, cosine squared theta, plus a to the fourth, sine to the fourth, phi, sine squared theta, plus a to the fourth, sine squared phi, cosine squared phi. And now I need my square root. And let's simplify this a little bit. Let's see, we've got cosine squared and sine squared, and notice we can factor out the a to the fourth, sine to the fourth. So that means that we're just going to have a to the fourth, sine to the fourth times 1. So that's a to the fourth, sine to the fourth, phi. And then we still have this part over here. So plus a to the fourth, sine squared phi, cosine squared phi. We still have our square root also. Okay, again, we've got, let's see, sine squared, a to the fourth sine squared phi is in both of these guys. So factoring that out, I have sine squared phi plus cosine squared phi. There's a square in here. So that means that's 1. So all I have left with is an a to the fourth sine to the fourth phi. A is positive, so I'll pull that out. So I've got a squared when I take the square root of a to the fourth. And I've got sine squared phi left inside. But phi is greater than or equal to 0. So that means that sine phi is greater than or equal to 0. So I've got a squared sine phi. I could take the square root without having to worry. I think we can finally get our surface area now. So that'll be the double integral over d of the length, magnitude of r phi cross r theta. And that'll be the integral from 0 to 2 pi, 0 to pi, a squared sine phi d theta, which is a squared times the integral from 0 to 2 pi d theta, and then the integral from 0 to pi of sine phi d phi, which is a squared times 2 pi times 2, which is 4 pi a squared. If a surface S has equation z equals f of xy, in other words, z is a function of x and y, which is not usually the case, then we have a another formula for our surface area. And notice how similar this is to what we got for the area of a surface of revolution, square root of 1 plus the derivative squared. So to prove this, it's actually pretty easy. We just take x and y as parameters, because we can, because z is a function of x and y. And then the partial of r with respect to x will be I plus the partial of f with respect to x times k, because partial of x with respect to x is just 1, so we get 1i. And notice that partial of y with respect to x is 0, so we don't have any j's. Similarly, for the partial of r with respect to y, we get 1j plus the partial of f with respect to y. So that means that we'll take our cross product, and taking our determinant of our matrix, we just get minus the partial of f with respect to xi minus the partial of f with respect to yj plus 1k. So we'll take those components, we'll square them, and take the square root to get the length. So we just get this for the length. But we'll just put z in instead of f, and we'll move the 1 to the front, and then we have our formula right over here. So let's do a quick example. We'll find the area of the part of the paraboloid z equals x squared plus y squared that lies under the plane z equals 9. So how about we quickly draw that? So here's our paraboloid, and let's see, our z-axis has to poke out, and it cuts off at 9. And we'll have an x-axis and a y-axis. And now we can draw our domain. It's like this shadow over here in the xy plane. And it's this region, let's call it D, where it's going to be x squared plus y squared equals 9, which is 3 squared, so then it's 3. Notice it's the shadow over here going down at 9, so since z equals 9, x squared plus y squared equals 9 over here. So we get that the radius is 3. Okay, so now we can do our area. That'll be the double integral over d of the square root of 1 plus each of these partials squared. So partial z with respect to x squared plus the partial of z with respect to y squared, and that'll be double integral over d of the square root of 1 plus, let's see, partial of this guy with respect to x is just 2x, and then the partial with respect to y is just 2y. So we get that this is the double integral of the square root of 1 plus 4 times x squared plus y squared. Notice that we're integrating over a circle, and we have x squared plus y squared inside, so this is a very natural candidate for polar coordinates. So let's convert. We'll get the integral from 0 to 2 pi for theta, and then our radius goes from 0 to 3, and the square root of 1 plus 4 times, well, x squared plus y squared is r squared. And then we have dA is r d theta. So this becomes the integral from 0 to 2 pi of d theta, because we can split it because we only have r's over here, times the integral from 0 to 3 of r times the square root of 1 plus 4r squared dr. So that's just 2 pi for my integral for theta times 1/8 times 2/3 times 1 plus 4r squared to the 3 over 2 power. Do a quick u substitution, and we evaluate from 0 to 3. So we just end up with pi over 6 times 37 rad 37 minus 1.